A spectrophotometer is an instrument that measures the amount of photons the intensity of light absorbs as it passes through a sample solution. With a spectrophotometer, various features of the sample may be determined, such as the concentration of the solution. It must be pointed out that visible light spectrophotometers are only useful for analyzing solutions that are colored. Here's how a spectrophotometer works. A light source, typically a bulb of some kind, shines light on a diffraction grating, which acts as a prism and splits the light into its component wavelengths. The grating can be rotated to direct the light towards the exit slit so that only light of a certain wavelength exits the slit and enters the sample. When the light passes through the sample, it reaches the detector to be analyzed. As the light enters the sample, the incident light may be absorbed by the sample. The absorption of the light depends upon the structure of the sample molecules, the width of the container, and the concentration of the solution. If any light is absorbed, the intensity will change. The fraction of the light reaching the detector is called the transmittance. The percent transmittance is the transmittance times 100. The percent transmittance is converted to an absorbance measured by the device. The percent transmittance is inversely proportional to the absorbance. In short, higher transmittance means a lower absorbance. For example, if the percent transmittance is 100%, this means the light passed completely through the sample with no absorbance at all. If the percent transmittance is 0%, this means the light absorbed virtually, or the sample absorbed virtually all of the light. Understandably, neither of these scenarios would be very useful from an analytical standpoint. Optimally, the absorbance should be between 0 and 1.0 to obtain the most accurate results. Solutions containing transition metals are often colored. This is because of the presence of unfilled d orbitals in the atoms or ions. Copper 2+ ions are usually blue in aqueous solutions. These unfilled d orbitals are usually degenerate or of equal energy in copper ions alone. But when copper 2+ ions are surrounded by ligands such as water molecules in solutions, the d orbitals split into orbitals of different energy. When certain photons of light strike the sample containing these ions, d to d electronic transitions become possible as the ion absorbs the energy. This corresponds to light in a particular wavelength. But what does this have to do with color? The diagram on the screen is called a complementary color wheel, which is very useful in explaining the phenomenon of color. Consider an object like a banana, which of course appears yellow. The reason it appears yellow is because it absorbs the color that is complementary to yellow, that being violet, as well as other colors around violet to lesser and lesser degrees. Whatever is not absorbed is transmitted back to the observer's eye. So to the observer, the object appears mostly yellow, and to lesser and lesser degrees the other colors around yellow. If we consider a compound like FDC red number 40, which is widely used as a synthetic dye, of course it appears red. It appears so because the molecule absorbs mostly green light, as well as other colors around red to lesser degrees. If we measure the absorbance of FDC red number 40 at different wavelengths, we would see that it absorbs mostly around 535, which is what we call lambda max, which corresponds to green light. So FDC absorbs mostly green light and other colors around green to lesser degrees, and transmits back other colors that are not absorbed. Beta carotene, which is responsible for the color of carrots, absorbs mostly blue light and other colors around blue, and transmits back mostly orange light as well as other colors to lesser degrees. An examination of the corresponding absorbance versus wavelength graph of beta carotene bears this out. Zeaxanthin, another carotenoid found in foods like corn, paprika, and saffron, appears orange for the same reason as beta carotene. The factors that affect the absorbance of light are the following: the concentration of the sample, the pathway through the sample, as well as the structure of the molecules in the sample. The concentration of the solution refers to the number of solute particles in the sample per unit volume. Generally, having more particles in the solution will correspond to a greater absorbance. This is because more particles in solution will allow less light to reach the detector as it interacts with the sample. In other words, the intensity of the light reaching the detector will be lower in solutions containing more solute particles. Note that as the concentrations of the solutions increase in the diagram, the corresponding absorbance measurements increases in a linear fashion. The path length through the sample also affects the absorbance. Cuvettes or test tubes with larger path lengths allow for more interaction of the light with the sample molecules. Therefore, the sample molecules will absorb more light as it passes through the sample. And finally, the particular characteristics of the sample molecules themselves, namely their electronic or molecular structures, will determine the absorbance of the light in a particular range of the electromagnetic spectrum. All of these factors are encoded in the Beer-Lambert law, or simply Beer's law. The absorbance of the sample is equal to epsilon, or the molar absorptivity constant, times B, or the path length, times C, or the concentration of the solution. Pay special attention to the units and features of each variable on the screen. What Beer's law shows that if we plot the absorbances of solutions against their concentration, that is, if the solutions follows Beer's law, there is a linear relationship between the two variables. Since this plot follows the general form of a straight line, we see that the slope of the line corresponds to the product of the molar absorptivity constant and the path length through the sample. We will utilize this mathematical relationship in our lab. The purpose of the lab is to determine the concentration of a copper 2 nitrate solution using Beer's law and a spectrophotometer. The first thing we'll do is to determine the lambda max of the solution in order to know where in the visible range of the EM spectrum the sample absorbs. We will set the spectrophotometer to this wavelength. We will then generate what's called a calibration curve by measuring the absorbances of solutions of standard solutions of copper 2 nitrate of different concentration. The plot must result in a straight line in order to use Beer's law. The unknown solution will have a concentration somewhere in the range of the concentrations of the solutions in the calibration plot. Therefore, we could qualitatively estimate the concentration of the unknown solution by visual inspection. To quantitatively and thus more accurately determine the concentration of the unknown, we will use the calibration plot to determine the slope of the line, which corresponds to the product of epsilon and B. We will then measure the actual absorbance of the unknown sample. Using the absorbance and the slope of the line from the calibration plot, we can determine that the concentration of the solution is A divided by epsilon times B. Here's a sample problem. Using the calibration plot and the absorbance of the sample, calculate the concentration of the solution. The absorbance of the unknown sample is 0.883, the path length of the cuvette is 1.0 centimeters, and the equation of the plot is shown. Since we have the equation of the line, we know the slope. We know that the slope is 4.84 times 10 to the third. We can utilize the fact that the absorbance divided by epsilon times B equals C. Plugging in the information from our plot, we see that the concentration of the solution would correspond to 1.82 times 10 to the minus 4 molar.